Right, good evening. Welcome back to Hack in the Box Studio. We are towards the tail end of Hack in the Box Cyber Week 2021. My name is Saumil Shah, and for the final discussion with our guests, I am joined by two very near and dear friends of mine, Cristofaro Mune from Raelize. He's the co-founder of Raelize. Welcome to the studio, Cristofaro.
Thank you,
and a long-running friend of mine, Adam Laurie, who I've had the pleasure of knowing him as Major Malfunction. Adam works with IBM X-Force, and Adam and Cristofaro have, most graciously agreed to spend this time with us in the studio. We just pretty much going to have an informal conversation. Adam, I've known you since 1999.
Is it that long? Oh my God.
It's been that long.
Wow.
It's like you are out there as a DEF CON goon. You are the closest person I know who is like Q from James Bond, because you can do all those things and even more. And what's more, I've seen you do that, from replaying infrared signals from TV remotes, RFID doors, satellites, and every time I hear you speak, you're doing something completely different, and then you go like way deep into it. I would love to discuss more of your past research and your present research, what you're doing. Cristofaro, I've also known you as a good friend since many years. It was an honor that you were a student in my class at one point.
That's true.
And I wish to be a student in your class at some point in the not so far future, in fact, in the next couple of years. Cristofaro's been basically attacking several areas of this rectangle that we carry in our pockets, typically called a mobile device. Cristofaro and his colleague have worked extensively on attacking the trusted execution environment, typically known as trust zone, and also worked on secure boot and exploiting secure boot environments. To me, both your fields, like your wizardry with electromagnetic signals and radio frequencies, Adam, and your expertise in the layer below the operating system and slightly above the hardware, it's like a very thin layer that you operate on. These are areas unknown to me. I mean, I am a user space and a kernel guy, and then like my worldview ends over there. So one of my selfish reasons of bringing you in the studio is I just wanted to learn firsthand from you, what is it that brought you here, what is it that you do, and what are the next things to come. I know, Adam, I'll let you go first.
Well, it's kind of funny because most of the stuff, what you referenced in your introduction, and thank you, by the way, for inviting me. It's a real honor to be here. And lovely to see you again after so many months in isolation.
I know.
But most of the things that I look at are actually in plain sight. And it's like, even though you can't physically see them, the thing I always find amusing is the protocols that are being used that are so insecure are being transmitted in plain text, but because they're going via RF or infrared or, magic moonbeams, as I like to say, whatever, right. Because you can't see them, people assume they don't need to worry about the security. So my kind of speciality, I guess, is spotting these invisible signals that are actually right there for everyone to see if they just looked using the right technologies or the right spectrum.
So it's essentially just like the physical layer changes, right? It's a protocol. We're typically used to having it over the Ethernet or over maybe serial port, or if you're the cool kid, X.25.
Yeah.
But then you go above and beyond to anything that talks a protocol over any magic moonbeam.
Yeah, that's exactly right. So, things like Magstripes then became NFC, but the data that's being transmitted is exactly the same. Serial data connecting mobile phones in the early days where you physically plugged a cable in, then became infrared, then became Bluetooth. But the actual data and the conversation that's being had over those mediums are following the original plan, which was not secure because it's a directly connected physical wire, you're plugging a cable in, so that's a private conversation.
Right.
But then when it moved to infrared, suddenly it's a broadcast conversation, but they didn't add any security. So
essentially, anybody who rocks up with a device that emits those magic moonbeams can take over.
Exactly. You can sniff them, understand what's going on, and then rebroadcast them and take over.
And it's up to the protocol to figure out or the designers to think if this could possibly happen or not.
Yeah.
And then
so whenever there's a change of physical medium, they should also be they should step back and rethink, well, have I introduced a new attack surface? Or am I just going to take my existing protocol and present it to the world without any modifications, even though the attack surface has completely changed?
Yep.
So crazy.
And I can vouch for that because he's opened up hotel safes. He's changed photographs on passports while they were in the protective covers being shipped in transit. He's opened up training venue doors when I returned from lunch a little too early and there was no staff. And I really wanted to get in. So he's like pulled out his laptop, click, 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 door open, in you go. I've seen you do all that. It's like, you make it sound really easy, but to even a person like me, it's magic.
Thank you. But it's just being observant. We actually had this conversation last night over dinner, talking about being observant to the things that are going on around you. And that's probably one of the biggest sort of hacker mindset things, is that we don't just accept things for what they are. As soon as we see something, we want to understand, well, why does it behave like that? So when we see it again and it behaves differently, we notice the difference. Right. And then we're like, oh, well, something's not right there. It behaves slightly differently, so therefore. And that's that whole process is how you lead into breaking things.
I also attended your DVB tuner talk at one point where you were figuring out what type of satellite it might be, aiming it. At that time, I realized that what you mentioned is right. Like if you have a DVB tuner, that's great. You could get these signals, but then connecting them to generic software and scripts or tools that you can plug in and interface. Like, how easy is it for you to find drivers or adapters or shims for these?
Generally, it's pretty easy. And actually, I'm lazy. I'm one of the lazy hackers that tries not to write code when I don't have to.
Yep.
So you will find that the manufacturers of the hardware, of course, they want to sell it into a market and they want that market to be as big as possible. So generally they will, they'll write drivers for Linux or Windows or whatever. So you just have to do a bit of digging, and very often what you're dealing with is a white labeled product. So, right. The logo on the product might not be the actual manufacturer. So you do a bit of digging to figure out who really made it.
Who the OEM is.
Who the OEM is, and then go and find their software, and then, hey presto. And really, like all of us, I'm standing on the shoulders of giants. Other people have done the work for me. I'm just adding another little step using tools that were probably designed for something totally different, like building a set-top TV box for hotel networks to sell as a commercial product. And I say, oh, well, I could use that as a hacking tool. They've done 99% of the work for me. I just have to add this little 1% on top. So.
I mean, one other takeaway from seeing you in action was when you're brute forcing the hotel TV network. All you're doing is literally like playing out keys on the TV remote, figuring out what codes were being emitted, and then trying all the codes that were not being emitted.
Yeah.
That was the first time a light went off in my mind saying, this is what, inverse fuzzing is. And, but question to you is, that thing happened almost 20 years ago. It happened in Washington, D.C. I know that very well. And Q, our friend Q, was in that same room.
Yeah.
Why have things not changed?
That's such a good question.
I'd love to see you here, but why are we still here? Right?
We have this conversation. I mean, it's a running joke in our industry that we work really hard and yet nothing gets better. So what are we doing wrong? People make the same mistakes over and over again. They like to take the shortcut like we do. You know, as hackers, we take existing code and we build on it. The same is true of developers. The same is true of startups. You know, they have an idea. They want to get it to market as fast as possible. They just take what's come before and use that. So that comes with it a legacy of problems.
Right.
And, you know, people don't prioritize those problems. They're like, no, we get it to market first. We can worry about that later. And that's the same story we've been hearing for 20, 30 years. So.
Is proprietary also ironically a synonym for security? Because, you know, we make it, so ergo nobody's going to make it. So who the hell is going to find it?
Yeah. Security by obscurity never works. I'm a big believer in open source. That's what I've been since day one. And you know, you're seeing a lot of problems. Take Y2K, for example. That wasn't a security problem.
Yep.
That was an operational problem.
Yep.
In the open source world, all the problems were resolved like 2 years before the date change.
Right.
In the closed source world, up to the last minute, I mean, and beyond, they were fixing problems. So,
yeah, that's a great point. Cristofaro, after hearing, I mean, thank you for letting me in your training earlier this week. It was actually the first time I got to, another epiphany happened when you mentioned that we as exploit writers, I write exploits, I teach how to do that as well. We don't look at this dimension at all. We spend so much time breaking the exploit mitigation mechanisms that are put in place, but all you have to do is look at a layer below. We look at those read and write primitives that you mentioned, the whole trusted environment opened up in a way. I won't even begin to know where to look for these things. But that got me questioning that, is this thing that I'm carrying in my pocket so proudly being touted as, hey, you know, it's a very, very secure environment. Like, how insecure is it compared to an average PC?
I think that's also a very good question. Thank you, Samuel, for having me here. Honestly, I think that, like everything, is by default insecure, but the point is that it can be insecure in ways that you don't expect.
Right.
And that is the important part. Honestly, one of my favorite things, I think if I should describe what I like to do in a nutshell, is I like failing assumptions.
Okay. Yes.
So basically, there is an entire world of people who actually look for software vulnerability, how to exploit in a common way. We have a very broad literature now of techniques and so on. But those techniques have been built mostly under the assumption that you have one CPU executing code, that you have some memory that is being used for such tasks, and basically that's it. This is not anymore like this since like at least 20 years. We don't live under the illusion of only one core.
Right.
We have already 12. Our systems are so much complex that thinking that they have only one CPU because we want to think like that, it's again an illusion. So nowadays, basically, what you have in hand is a very complex system. And you think that the part you should secure of that is only what is executed on the main CPU. Right. So there are many ways of failing that illusion that are way beyond your single CPU, which you have the layers below, but you have also the components which are outside of your CPU, which may fail the security boundary. So basically, your security model only exists. It's an illusion of your CPU. It's not a system-level illusion. So this means that the system may completely disregard what you think is the security model. That is not the security model of the phone. That is the security model that runs on your CPU that you would like to see.
This, I opened up my introduction saying that I am a user space and kernel guy, and this is exactly what I've been trained in. Like, I have been seeing this diagram that here's the software, here's the kernel, here's the CPU, and here are the peripherals. I only see that rectangle, and like,
it's a silo.
It's
a silo. So basically, like the CPU that we usually discuss, that we typically use and we see the result from, well, there are many others. For example, think about having an Ethernet controller on a device. You have also, in many cases, Wi-Fi SOC, which is an entire SOC, which executes code. You have a baseband. You have a GPU, which still executes code. You have a video decoder, which has firmware. You have an audio decoder, which has firmware. So there are many of these devices which are firmware. So we call them execution units because they're able to execute code. When you think about not CPU, but execution units, think about that there may be tens which are running concurrently to your CPU that you think should be secured, where there are only two solutions. Either you are aware and you are scared of, or you are simply just forgetting about it. This is actually a good situation, and this is why I like to dig into failing as this assumption of the security model by looking broadly, like different components, like in trust zone, by looking at lower layers, like in bootloaders, or by the way, also we have something in common with Adam. We like a lot fault injection.
Yes.
Basically. And in the case, we are failing the model where an instruction is executed by CPU correctly. And not only, even by the hardware itself. So I would say that now, after this short, let's say, introduction, I think that I would say myself that I like failing assumptions.
Yep, that's great. And I saw your stuff in action at the last Cyber Week as well, where you showed me glitching, and that also opened up my eyes. Like, honestly, the reason why I go to conferences is this is where I learn. Right? This is where I get new ideas. Of course, it's lovely to see friends. This is the only opportunity I get to learn. This is what keeps me going. So what's next, Adam? What are you working on?
So what I was presenting here today was, again, a protocol that's being transmitted over thin air and is surprisingly not secured, not encrypted, not authorized or verified, and it's time synchronization. So basically, we all take for granted that you can tell the time, you can look at your watch, but at some point you had to set that watch to the right time. So you will have got that from somewhere, like a network clock or your laptop clock, which is in turn synchronized to an atomic clock somewhere. So what I'm looking at is, well, how is the atomic clock signal transmitted to the global consumer base, which isn't just us consumers, it's banking, high-speed trading, transport networks, communications networks, everything relies on the security of a completely unsecured protocol. So it's like...
So we're like one step closer to tomorrow never dies.
There's so many disaster scenarios we could bring into the equation. It's not funny. And for me, what was the most interesting thing is that nobody's really talking about it in this community and in this environment.
Yeah.
I mean, yes, there's a lot of government agencies and people who are responsible for the infrastructure who put the satellites with the atomic clocks up into space. They're talking about it. They know it's a problem, but the people who are actually on the front line defending from these things, which is us, we've talked about things not getting better for 20 years,
yes,
but it gets better incrementally because people like Cristofaro and you and all my peers here actually go out there and spend their day trying to find these little problems. We're on the front line, and yet we're not talking about this, and that really surprised me when I looked into it.
I fully agree, definitely. I think that the part where we are simply disregarding complexity or ongoing complexity, I think is in a way maybe just a way that we are learned for coping with technology. Maybe it's could be something, but for sure we are not discussing many things which could be definitely relevant and dangerous in some cases.
Yeah, I mean, it's strange. It's become ubiquitous not through design, but just because it's there, and because it's cheap, and because it's easy, and because everyone just took it for granted. So entire infrastructures are built on these single points of failure that nobody has addressed literally until a year ago. So
in the end, it just boils down to that you just not factored it in into your threat model.
These protocol, NTP, which is the network time protocol, is one of the oldest protocols on the internet.
Yes.
And yet it was only, the idea of adding crypto to it was only ratified a year ago.
Right.
So, you've got PTP, which is a secure time protocol. But again, it's just a distribution method. It's not the source of the accurate time. That source is still coming to it over plain text, either from satellite or from RF or whatever, across the network through TV broadcast.
Yeah, I mean, I can see the possibilities.
Once you notice it, it's like,
Yikes.
really? Yikes. So, yeah, sorry about that. If everything breaks tomorrow.
Everything breaks tomorrow, no doubt. And Cristofaro, what are your next steps? Greetings to Nick.
Thank
Nick,
you.
if you're viewing this. Hi, we miss you.
Hi, Nick. Hi, everybody.
What are the two of you going to do? Realize?
So we like bringing, say, the frontier of fault injection a bit, pushing it a bit forward. For example, we have been doing, would like to continue, the implication of a fault model which is called instruction corruption. To give you an idea, with this, during the last few years, we went from user space to kernel PC control with just one single glitch. Right. Precise PC control. So we can say to the PC program counter, just go here, 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 with, let's say, extremely precise resolution without any problem. With this technique, we have been able to bypass an encrypted secure boot without having keys.
It's brilliant.
So,
just make it jump over it.
Yeah, so basically we were able to bypass the secure boot and the encryption, sidestepping them with one single glitch, and we don't need keys.
Wow.
Why would you need keys? And this is possible because of the fault model that which has not been explored, let's say, in the way we like. We think there is more to be done there. So fault injection is for sure one thing. And we're seeing more complexity which are coming into a trusted execution environment. For example, in the last couple of years, what we have achieved, for example, is that we are running concurrent trusted application and code on the TE side. So this means that the race conditions which were only something available, mostly in, on the RE side, kernel, user space, and so on, now they may be transferring also to the TE side. And it is something that opens up an amount of research of things that we would like to explore, which is interesting. These are mainly the kind of things, and we also see, what's the other part is that we see more and more of these security features, secure boots and trust NTEs, being surfacing in devices which are really cheap and simple. So nowadays you can buy a $5 SOC system on chip which has secure boot and a trust zone on top. So this means that we'll find them everywhere, even if we don't use them.
Yeah, it's going to be here.
So there are many opportunities there which we find interesting for sure.
That's awesome. And well, I know for one thing for sure, the next time I see you folks, I'm going to learn something something new, something completely different. And I'm personally excited. With this, I would like to thank you, both of you, for joining me in the HIDB studio. Thanks very much. It was
Thank you.
So awesome
for the invitation.
Thank you. It was
Great pleasure.
Great.
Thank you.